Welcome to part 3 on my series on exponential rules. Today we're going to talk about negative exponents. Now I'm going to read rule 5 out, and it's a little bit wordy, but I will break down the entire rule and show you exactly what each word means. So, a base raised to a negative exponent. So if I have some base raised to a negative exponent, has the same value as the reciprocal of the base to the positive of the exponent. Now, that's an awkward way of putting this, but as many of you have already noticed, sometimes it can be very difficult to talk accurately about these ideas without sounding a little bit weird, right? So what it means is you take the base and make it reciprocal to the positive of the exponent. So this is negative, this is the positive of that number. And of course, because of our distribution rules, which we learned in the last video, that's the same thing as 1 over a to the n. Right? Because you can distribute this, 1 to the n is just 1, a to the n is a to the n. So that's our rule. And as always, let's do some examples. So if I have a to the negative 4th, and I want to express that with only positive exponents. In fact, we're only going to express our answers with positive exponents. So a to the negative 4th, well, that's 1 over a to the 4th. Essentially, remember this a to the negative 4th is over 1. Essentially, I can move from the top to the bottom so long as I change the sign of the exponent. Let's do another one. 1 over 10 to the negative 4th. Well, this works backwards as well. At the moment, I have 10 to the negative 4th on the bottom. The reciprocal would be to have it on the top. Again, I move from the denominator to the numerator and change the sign of the exponent. So our answer is 10 to the 4th. Let's try one that's a touch more complicated. 2/3 to the negative 3 power. Okay? 2/3 to the negative 3 power. Well, that's the same thing, based on our rule up here, as the reciprocal of 2/3, which is 3 over 2, to the positive 3 power. And then we can go back to our rules from the last video. Well, that's 3 to the 3rd power over 2 to the 3rd power. Do not say 9 over 6. 3 to the 3rd power, well, 3 times 3 is 9, times 3 again is 27. 2 times 2 is 4, times 2 again is 8. Our answer is 27 over 8. Let's try one that's going to look really, really weird at first. Let's do something super duper complicated, like 5 to the 3rd x to the negative 4.
Or y to the 2, z to the negative 1, all divided by, I don't know, 5 to the negative 3, x, y to the 6, z to the negative 4.
I don't know, something big and horrible looking like that. But again, this looks bad, but let's take it one teensy-weensy little step at a time, shall we? Now, there are a bunch of different ways you can look at this. What I'm going to do is I'm going to look at each base as a subproblem, and I'm going to solve each one out individually. This is all division, right? So I get 5 to the 3, again, be careful, minus negative 3. So that gives me 5 to the positive 6 power. How about these x's? We have x to the negative 4th. Now, what's the exponent on this x down here? Well, that's x to the 1. So you have negative 4 minus 1. Again, if I'm at negative 4 and I go down another one, That gets me to negative 5. Now we'll combine all of these in a second. How about the y's? Y to the 2 minus 6. 2 minus 6, if I'm at positive 2 and I go down 6, that's 1, 0, negative 1, negative 2, negative 3, negative 4. Yes, I just counted on my fingers. I know you couldn't see it, but that's what I did. Don't be afraid to count on your fingers. That's what they're for. How about z? I don't know why I put equals there. Z to the minus 1 minus negative 4. Well, if I'm at negative 1, now that minus negative means I'm going up. So if I'm at negative 1 and I go up 4, that's 0, 1, 2, 3. Z to the positive 3. So now that we've gotten each little subproblem dealt with, we've got 5 to the 6th, x to the negative 5th, y to the negative 4th, z to the 3rd is our answer. But the problem does specify that we want positive exponents only. So, keeping in mind that this is all over 1, everything is always over 1, we're going to take our negative exponents and move them on down. So that 5 to the 6th stays on top, the z to the 3rd stays on top, the x to the negative 5 drops to the bottom and becomes x to the positive 5. The y to the negative 4th drops to the bottom and becomes y to the positive 4th. That's about as complicated as these problems get. Now, we have one more rule, and I'm not even sure I really call it a rule as much as a corollary. In math, a corollary is a connected theorem. And I feel like what I'm about to say is a corollary to what we've just learned. So this corollary, I'm going to go ahead and call it Rule 5a. Any non-zero number to the 0th power, any non-zero number to the 0th power is equal to 1. Okay? And it makes sense from a lot of perspectives. We talked in class about how if multiplying means adding 1 to the exponent, then dividing means subtracting 1 from the exponent. So anytime you get to the 0th exponent, you are dividing a number by itself to get to 1. But it also makes sense in the context of the rules we've just learned. Check this out. If I have x to the 5th divided by x to the 5th, yeah? Well, we already know that anything divided by itself is 1, right? Anything that's not 0. Again, non-zero. But we also know that this is x to the 5 minus 5, which means x to the 0. X to the 0 equals 1. Very quick, very simple proof. In fact, we could even do it with generic numbers, right? We could say a to the n divided by a to the n equals a to the n minus n equals a to the 0, but also anything divided by itself does indeed equal 1. It's a seemingly unimportant rule, but it is something that especially standardized tests love to mess with you using. For example, they'll say something like, hey, here's x to the 5th, y to the 12th, z to the 27th, divided by blah, 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 and then they'll raise the whole thing to the 0, and the moment it's to the 0, it equals 1, and they're going to laugh at you for doing all that work. So be on the lookout for that sort of thing. Anything to the 0 power, no matter how complicated, so long as it's not 0, equals 1. Now, I do want to address 0 to the 0 really quick. I want to address that really quick because if you plug this into your calculator, I'm pretty sure your calculator will say 1 if you plug it in there. The problem is, if you say 0 to the 0, you're essentially saying, based on our rules, 0 to the, let's say, 1 minus 1 power, right? Which means 0 divided by 0. And there's your problem right there. You can't divide by 0. You just can't. It is an indeterminate value. And in calculus, we learn that 0 over 0 could be just about anything. In fact, I believe it could be literally anything. Any number that you can imagine, 0 over 0, could theoretically, in the right circumstances, equal that number. So try to wrap your brain around that one. And that's it for this video. I have one more video on exponent rules coming out. It will be the video on fraction exponents and square roots and radicals. If you have any questions, please do leave them in the comments. I will be happy to address them there or via email or just raise your hand in class. And until next time.